All right, so we're at our last video for Unit 3, and this is just kind of pulling it all together. We did optimization in video 8, and that was kind of a real-world moment about using the first derivative and second derivative. And now we're going to do the same thing, a real-world application, looking at velocity of a particle or an object and acceleration. Now, you already know from stuff we've done in the past that velocity refers to the speed of an object, and acceleration is how fast that object is speeding up or slowing down. So how fast the velocity is changing. So to make a couple of quick notes that are important, we let our position of our value be x of t. And the velocity of that then would be the derivative because you want the speed of your object. So we'll write that as v of t, but just realize that it's just the first derivative. And then if I want this acceleration of an object, I want to know how fast it's changing. That's really the derivative of the velocity, or in general, the second derivative. So that's acceleration. The speed of a particle is always the absolute value because we can refer to something as having a negative speed in a drawing, meaning that it's losing ground. But in general, if I'm asking you what the speed is of something, you would just give it to me as a positive value. So like if something was moving at a rate of 20 feet per second, you would say that rather than negative, meaning it's like coming back to something. So it's always positive. If I want to know whether an object is speeding up, so if its speed is getting faster, then if the velocity and the acceleration have the same sign, meaning that both of them are positive or both negative, it's speeding up. And if they're opposite signs, then that object is slowing down. So let's take a look at a couple of examples of that. So in this first example, we're just doing a general graph. Eventually, we'll apply these to word problems, but we have an object according to x of t on the coordinate line. So here's my position. So if I wanted to put in if I wanted to know what the position of my object was after 2 seconds, I could plug in t equals 2, and that would give me the actual position on the number line. And we are in centimeters and seconds. If I want to find the velocity of my particle at 1, velocity would be, I want to find the derivative. So the first thing I would have to do is find the derivative of this equation. So you can either write that as x prime of t, or you can write that as v of t. That's how I will typically write it. The derivative here is just 3t squared minus 24t plus 36. So this is where your notation is important, guys. So if I want to find the velocity at time equals 1, you should show this. And what I get when I plug in 1, and you can do that work on your own, is 15. So what does that mean? Velocity is always in distance per time, so centimeters per second. B, if I want the acceleration, that means I want the derivative of the velocity. That's what acceleration is, or technically the second derivative of the original. So the derivative of this guy is 6t minus 24. So then I'm plugging into my acceleration the value 1. So the acceleration after 1 second, plug that guy in, negative 18. Now, acceleration is units per time squared because you're seeing the speed of the speed. Okay, so then the last question is it speeding up or slowing down? Well, because my velocity is positive but my acceleration is negative, I'm slowing down. And if it asked you why, you could literally say those two things. All right, so for example 2, I have a sketch. Now, this is really important to note. This is already velocity, folks, which means this is already the first derivative. I'll put that in terms of ours. This is already the derivative of the position. Remember that. That's important because sometimes this is x of t. Okay, so the graph given is the velocity already. It's from 0 to 55. The question is, when is the object at rest? Well, the object would be at rest when its derivative or its velocity is 0 because it would have no speed. So when is it at rest? Obviously at the beginning, but then it's at rest at 30, time equals 30, and time equals 55. So technically, I have at rest at t equals 0, 30, and 55. What is the object's acceleration at t equals 20? Well, remember, acceleration refers to the derivative of the velocity, which means I would want the slope of the velocity equation at t equals 20. So I'm going to go over to t equals 20. Here's my point I'm going through. The nice thing about this is it is a straight line, so I can find the slope of that line. Now be careful when calculating slope. Um, Typically, people will use the beginning and the ending of a straight line because you can't always tell exactly where it hits. So a lot of times people will use this value right here and the end of that straight line, but you can use any 2 points. So my slope here looks like I'm going down 20. Be careful about your x-axis. And this is going by 5. So just be really careful about your scale. So my slope through that value is down 20 over 5 or -4. And again, I'm looking for acceleration, so it would be -4 minutes, or excuse me, meters per minute squared because I'm in acceleration. Okay. Um, Last but not least, I want to know at time equals 50, is it speeding up or slowing down? Well, we already know what the acceleration is by finding slope. Well, actually, we'll have to find it, but let's find the acceleration at 50, which means I want the slope through the point 50. So here's 50, which means I want the slope here. So my slope looks like I go up 40 over 5, 10, 15. So I can reduce that by 5 on top and bottom. So I get 8/3. Now, again, I don't really care because to find speeding up or slowing down, I'm just looking if it's positive or negative, but it is 8/3 meters per minute squared. I also need to find the velocity at 50 so I can compare. The velocity at 50, since this already is the velocity graph, just is what the value is, which is something that's negative. I don't actually care how much it is. I just care that it's a negative number. If this is positive, your acceleration, and your velocity is negative, then because they're opposites, this is slowing down. All right, and our last example shows you how we can do this on the calculator. So once again, we're given in a relationship for a particle moving, we're given the velocity. So we're going to graph this guy and then we're going to find some information. So let's take out that calculator and take a look at what we've got here. I already went ahead and graphed it. So I'm going to start by finding the velocity at t equals 1. That's the easiest one. So here's this. By the way, it did say it was only going from 0 to 3. So I made sure that my window just went from 0 to 3. Okay, so here's my graph. So if I want to know what the derivative is or what the velocity is at 1, that just means plug in 1. Since 1's so nice, I could, of course, go to my table and get the general idea. But what if it's not nice? So if you go back to your graph and you just hit trace, trace can allow you to plug in any value. Like I can hit 1 and hit enter, and it'll give me the value. Most of you are more comfortable, though, going to second calc, choosing value, and then saying 1. So the derivative, if I just plugged 1 into my velocity equation, is -1.315. So A is the velocity at 1 is -1.3. I think we said 1.5. Yeah. Okay. For B, what's my acceleration? Well, if I want the acceleration at 1, I really want the derivative of the velocity at 1, right? We've talked about finding the derivative before using our calculator. But there's actually a shortcut to, if you just want to find the derivative of a graph at a value, you can do that using your calculate. So if I want the acceleration, I want the derivative of this graph or the derivative of that function. So if I go to second calc, I can choose this guy 6, and that will allow me to find the derivative of an x value of a given graph. So if I want the acceleration, again, I want the derivative of the velocity at 1. So I'm going to say find the derivative at 1. And then it'll tell me right here, the derivative at 1 is -2.529. So then the last part of this is the point P or the particle P speeding up or slowing down at 1? Well, again, because, and this is where if you wanted to get technical, this is something you could say. This is negative, and the velocity at 1 is negative, and the acceleration at 1 is negative. So it's speeding up because they're the same sign. Okay, you've got a lot of good problems to try, and I'll see you in class.